So this class is called Electron Movements. So remember last time we left off on just getting to the atom, you know. So now we're starting to break down. How you doing, Mr. Manny? So first thing is that atoms exist. Einstein proved to the scientific world once and for all that atoms exist. If you remember, talking about Brownian motion, little grain of pollen moving around, him using the statistical methods, all these things he kind of pulled together to make it really simple and easy. Also, light was shown to be both a particle and a wave. You know, so at this point, everybody's just like, what is it? Is it a wave? Is it a particle? Is it both? Do we not know? Is there a third thing that we haven't yet found? So the first thing we want to know is, now that we know atoms are real, then what is their structure? Now that they're confirmed to exist, the next question are, what are they composed of? So the British physicist J.J. Thomson, he did groundbreaking work on the discovery of the electron. Now, there's a lot of controversy concerning the nature of the radiation that is produced from a wire that carries an electric current through a vacuum tube. So, if you think about an atom and how impossibly small it is, and then you start thinking about the pieces of an atom, which are impossibly even smaller than that, you have to wonder, how are they even breaking these down into small pieces? And what they did is, they started studying cathode rays. And I'm going to actually show you. I found a whole bunch of YouTube clips, but I found a really good YouTube clip where this guy he did it just like he did it, like 150 years ago or whatever. He just went old school, and it was really cool. So cathode rays, and they should sound familiar because cathode ray tubes are, the boob tube, glass TV, radiation as it was called, might be a form of radiation produced by vibrations in the ether. Remember, right now they're like, is there ether? Is there not ether? Now that light's been proven a particle, you think ether's gone. But we know ether, if light is a wave, we can't explain how light can be a wave unless the ether is there. So right now scientists they're all over the place. There's ether, there's not ether, we don't know what it is. Or they could be seeing a stream of tiny particles. Now, most of the German physicists subscribe to ether waves, while most British and French scientists thought the cathode rays must be particles. So Thomson worked at the Cavendish Laboratory. Remember Henry Cavendish? He started, he was the genius who weighed the Earth. That was Class 2. He started a top-notch school just for physics. And they've been at the top of their game for 150 years. Every Nobel Prize winner went there for 30 plus years, and still now they're doing cutting edge research. He also established a research center in Cambridge, and it was established with Maxwell as well. And J.J. Thomson was the first Cavendish professor of physics, and he was able to calculate the mass of an electron. How did he do this? So the path of such a particle can be deflected both by the magnetic and electric fields, and Thomson's apparatus was designed so that these two effects cancel each other out, and he left a beam of cathode rays that traveled straight from a negatively charged metal plate. This is all really boring. I should show you the experiment first, but let me just finish reading it. So the trick only works for electrically charged particles. So Thomson established that cathode rays are indeed negatively charged particles. All right, so what do I mean? Oh, man. Really? Okay, let me skip this slide, okay? Let me just show you an example first. So I don't know if you've seen these before. This isn't like the ones like those globes where you kind of touch it. But basically, this is like a ray, Now, it looks ethereal, and depending on your voltage, it sort of moves, and it can do different things. So this is where they're like, whoa, whoa, whoa. Maybe we're seeing something go through the ether. It's like something going through the mist, Where the other guys were like, no. We're just seeing electrons because you're taking two pieces of metal and you're running a really high voltage. And if many of you may or may not know that electricity is the movement of electrons. Right. So between these two mediums, the electrons are basically shooting out into a ray. And these rays can be manipulated. So what J.J. Thomson did is he built an apparatus. Here's his cathode ray tube. And it was shooting a cathode ray through. And then he took a magnet, which is in the middle. And I'll show you a picture of it. But with the magnet, he was able to deflect it. So if he took the positive side of a magnet, just the ray bent towards it. If he took the negative side, it repelled, which showed him that not only whatever he was dealing with, it was negatively charged. So that's how we get that electrons have a negative charge. So here's the video, and this just kind of explains it all. I probably should show this first.
Hey guys, this is Goofer King Science, and today I'm going to be showing you my homemade cathode ray tube project. The vacuum pump I'm using here is made out of an old refrigerator compressor. The power supply is made using a variac and an oil burner ignition transformer. The variac, also known as an auto transformer, allows you to vary the voltage coming from a wall outlet without altering the waveform. The output of the variac goes directly into the oil burner ignition transformer. Normally, an oil burner ignition transformer takes in 120 volts AC and steps it up to about 10,000 volts AC at 23 milliamps. But when I vary the voltage coming into it, I can either lower or raise the voltage coming out. The actual cathode ray tube was built using a wine bottle and some stainless steel wire. I drilled a hole into the side of the glass bottle carefully using a glass drill bit and inserted a wire bent in a half circle shape. Then I secured it with hot glue to make sure it was vacuum proof. As you can see, I made two of them, and they each have the wire at different lengths down the tube. To create a vacuum inside of the wine bottle, I just attached a hose barb into the vacuum hose and slipped a rubber O-ring over it. When the vacuum is pulled, the rubber O-ring sucks down onto the bottle and it just seals itself. This way there is no epoxy or glues needed. Now it's time to power up the cathode ray tube. To do this, we need to attach some electrodes to the terminals of the oil burner ignition transformer. Next, we simply attach one of the other ends to an exposed piece of the hose barb and the other to that wire we added into the wine bottle. Now I turn on the variac and slowly and carefully turn up the voltage. As you can see, a beam of electrons, also known as a cathode ray, appears. It glows a bright purple color in my case due to small amounts of nitrogen and oxygen that are still left in the tube. Now I'm going to demonstrate the magnetic deflection property of a cathode ray tube. Since it is a beam of electrons, it can be influenced by a magnet since electrons have a negative charge. Here I have a few magnets, and one side is marked with tape. When I put one side of the magnet that is marked up to the beam, it bends around it to the right. When I put the unmarked side to it, it bends around it to the left.
And there you have it. Really simple, very easy to explain, and it's literally what's happening is just like a positive and negative terminal. The one terminal was on the hose, the other one was on the wire, and they sucked out all the air. Now there's still trace elements in the air. Right. So now you create a very, 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 very high voltage. And if any of you, we didn't go over electricity, but a voltage is a potential difference. So it's a potential difference in two things. And the voltage is so high that literally they actually are able to make a connection and the electrons flow. Just like they do through a wire, but they're flowing through air. They want to get there so bad that they're ejecting out and they're flowing through. And then he could see with the magnet, like, wow, these things clearly have a negative charge, and that was new. And on top of that, he was also able to ascertain, based on complex calculations, how much the electron weighed. Because they knew how much, at this time they were weighing everything. They were trying to figure out what is everything. So they were weighing atoms, getting their atomic weight, even though they didn't know, most people believe atoms were indivisible. This was the first time, and he was like, wait a minute, I'm finding something new. It's lighter than the atom, and it has a charge, and so it's obviously a piece of an atom. He studied them using a modified cathode ray. Oh, this is ions. We're studying ions as well. He studied them using a modified cathode ray tube in which a little gas was left behind by a vacuum pump. These electrons moving through the gas collided with the atoms and knocked other electrons out of them, leaving positively charged ions which can be manipulated with electric and magnetic fields the same way Thomson manipulated electrons. Thomson had enough information to produce the first stab at an explanation of what an atom might be like inside. Not an indivisible ultimate particle, but a mixture of positive and negative charges from which electrons could be chipped away. So, while electrons turned out to be negatively charged, or put it this way, he now finds little pieces of an atom, right? So let's say he's looking at hydrogen. He knows hydrogen weighs 50 pounds, right? And then he has an electron, and he knows an electron weighs 1,000th of a pound. So it's so much smaller than what this thing weighs. In addition, he knows that the electrons are negative. But they also know that atoms are neutral. Atoms in their stable state, when the chemists are working with them, are neutral. They're not positive or negative. So, if atoms are electrically neutral, so logically there must be a positively charged counterpart. There has to be something else in the atom that's positive to offset the negative electrons. Electrons are negatively charged. So, being British, and the British love plum pudding, he envisioned the atom like a cup of plum pudding, which a large space through which all the positive charge was spread, and the small electrons were embedded in it like negatively charged raisins. So here you see the big plus. So the positive charge is all spread throughout, and there's a lot of it, a lot more than the negative. And the negative are kind of spread there. So all the negative is offset by the positive, and as a whole, it's neutral. It's not plus or minus. Does it all make sense? So this is how he saw it. But not all scientists accepted this model, and there's good reason why. Rutherford didn't. The reason is he ran a series of experiments to test this model of the atom, and found that this model didn't fit with the facts. His model of the atom is what we're familiar with today, the orbital model of the atom. Now, raise your hand if you're familiar with this. You've all seen electrons, they go around, this is the basic model. He thought that all the positive charge in the atom resided in a concentrated nucleus, is what he called it, in the center of the atom, and that the negatively charged electrons orbited around the nucleus like planets around the sun. So how did he come up with this? Just wake up one day and have a revelation? He performed his famous gold foil experiment. So what he did is he made use of the newly discovered alpha particles and their ejection from certain types of atoms at high rates. Now, at this time, they had just discovered radiation. They had just discovered X-rays. Scientists had accidentally exposed things, and Madame Curie was finding you could X-rays and you could show bone. All this exciting stuff was going, and so they had a lot of tools, but they didn't know what they were. So an alpha particle, let me just tell you what it is. They didn't know what it was. They just knew an alpha particle was the simplest, smallest, lightest thing possible. So this is a hydrogen atom. The hydrogen is the most basic atom on the periodic table. It has one proton and one electron, no neutrons. All right? An alpha particle is, if you strip away the electron, that's an alpha particle. So an alpha particle is a hydrogen nucleus, or it's a proton. An alpha particle is a proton, just one proton. Now, nobody knows what protons are yet, and I'm just giving you a little ahead of myself, but he had access and was able to, with certain radioactive elements and doing other experiments that other people worked on, he was able to know about alpha particles, and he was able to shoot them, shoot them out. And they did different things with them, because that's what radiation is. You're shooting stuff, and it's going through stuff. And it makes sense here in the experiment. So the study of radiation had only begun, and while they identified alpha particles or beta particles, those are the two that are okay. Gamma particles, you don't want to mess with those. No one quite knew what they were. They also knew that alpha particles had a mass 2,000 times that of an electron. So they knew that the nucleus of a hydrogen atom, or any atom, is massive. Like 98 to 99% of the mass of an atom is all in the nucleus. Electrons don't really weigh anything. They have a weight. They're not weightless, but they're very, very light, which is amazing because that's what holds us all together. That's what holds matter together, is electrons. So next he prepared his gold foil. Now most of us are familiar with gold leafing. And many of us may not be aware that gold can be hammered so thinly that it can be actually hammered to 1 atom thick. I mean, it's crazy. This is from one of those famous French chateaus, And when I was in England, and I remember visiting a lot of the palaces, it was amazing how much gold. I mean, it was like, you thought it was like Solomon's temple, Now, they made clear it was all gold leaf. Yeah. And the artisans were so skilled, and I remember them saying this way back then, I didn't understand it, is like all that right there could be like literally like a 1/4 ounce of gold. Like an amount of gold that's equal to like a nickel. Yeah. And they were masked, because obviously you want to get the most bang for your buck. Okay, these aristocrats were gold leafing a lot of stuff. So this is important. So now I want you to imagine a sheet of gold that's 1 atom thick. So a wall of 1 atom, all right? So now what is he going to do? He's going to fire alpha particles at the gold foil. And he had a screen behind it to detect what happened and to measure the position of the particle, kind of like carbon paper. The atom left an impression in the paper. Now here's the funny thing. Remember, the model was plum pudding, right? So if you could imagine a proton as a bowling ball, that means an electron would be not even a ping pong ball, like a grain of sand. Like that's literally how much it is. So the grains, if the grains of sand were spread out evenly in the positive charge, then if you shoot a bowling ball, it should just go straight through, right? Like a bowling ball is not even going to flinch at a grain of sand. But look what happened instead. A lot of them, probably like 95% of them, 90+% of them went straight through, just like he expected. But then he saw weird stuff. Some of them, instead of going straight through, they were deflected at like light angles. Other ones, if you can see here, were deflected at hard angles. And then you had protons that were deflected back. And he had a large percentage, actually, that were deflected literally all the way back. Or he had some on this rim here. So they were like, okay, wait a minute, this doesn't make sense. And that's how he formulated his model of the atom. He's like, no. Positive charge can't just be spread out. It must be concentrated in a really, really, really tight spot. Because I'm shooting bowling balls. And whatever it's hitting, if it's bouncing straight back or it's bouncing back at a hard angle, whatever it's hitting is much bigger than it is. And remember, this is gold. Gold has 71 protons. So it has a very large nucleus as opposed to 1 proton. Now, what he expected to happen was to have the alpha, that's just what I said. Okay. So here's another diagram you can see. So if most of the atom is just this empty space, or electrons, or whatever, the protons are just, you can see they're just going to go straight through. The protons have charge, so if you get close to them, they could push them away or attract them. So you can see when the lines get close, they sort of bend. Now, obviously, if you happen to hit one of the nucleuses, bam, you're going to bounce back, depending on your angle. Remember, these things are just sort of shooting wild, you know. However, a small percentage bounced off the foil at varying degrees. Some fired back in completely the opposite direction. And here's a blow-up of that. And here you can see it here. And that's what the genius is because if the gold, if it was like 25 layers of atom thick, which is nothing, but that's a lot to a proton, the whole experiment wouldn't give you as much data. But since gold, one of the properties of gold is a precious metal for a reason, people, you know. Just from everything. It doesn't tarnish. It doesn't, you know, they found gold coins under the ocean for 100 years. And just, there they are, you know. So all the positive charge, therefore, had to be concentrated in a tightly packed ball or nucleus. The rest of the atom was mostly empty space. 99% of the mass of the atom is held in the nucleus. So Rutherford was also the first person to transmute one element into another. Now, transmutation is like the holy grail of alchemists or the early chemists, because what do they want to do? They want to turn lead into gold. So transmutation is when you take one thing and turn it into another thing. Now, they were never able to achieve this. No one ever achieved this till now. And so in the lab, and he wasn't turning lead to gold, using pure nitrogen, Rutherford used alpha radiation to convert nitrogen into oxygen. So nitrogen, we'll find later, has 7 protons and electrons, and oxygen has 8 protons and electrons. Right. He didn't fully know this. So what is he shooting? He's shooting protons. So if you're able to get a nitrogen to merge and grab a proton, it's going to become something completely new. In this case, nitrogen becomes oxygen. Now, why was this important for him? In the products of these reactions, Rutherford simply identified hydrogen nuclei, or protons, by their similarity to the particle radiation from earlier experiments, in which he bombarded hydrogen gas with alpha particles to knock hydrogen nuclei out of the hydrogen atoms. This is how he created alpha particles. This showed Rutherford that hydrogen nuclei were part of nitrogen. Now, he thought hydrogen nuclei were part of nitrogen, but later we realized, and he called hydrogen nuclei a proton. So now he knew that if there were protons in nitrogen, and it became oxygen, and there were protons in oxygen, then there's another fundamental particle. This proton is what has the positive charge. By implication, he surmised that hydrogen nuclei are part of all atoms. They have been suspected for many years based on the atomic weights, which were whole numbers of hydrogen. So they already knew now that they were weighing stuff, because if a hydrogen has one proton, right, and you could weigh that, let's say that's 1.5 pounds, whatever, and every other element has 2 protons, 3 protons, 4 protons, they saw pretty quickly that everything was a multiple of 1.5, or whatever hydrogen was. Because the electrons were so small, they don't even figure in your calculations. So they already knew that everything was a multiple of hydrogen, or something close to it. Of course, the multiples were compounded with neutrons, which they hadn't discovered yet. But neutrons are as heavy as protons, so it still doesn't matter. It's still the same multiplicative effect. So hydrogen was known to be the lightest element, and its nucleus presumably the lightest nuclei. So Rutherford decided that a hydrogen nucleus was possibly a fundamental building block of all nuclei, and possibly a fundamental particle as well, since nothing was found to be lighter than a hydrogen nucleus. So there's nothing smaller than this hydrogen nucleus. And then he found the next smallest piece, which is the electron, which was part of hydrogen as well. So in 1920, Rutherford postulated that hydrogen nuclei to be a fundamental particle, and he called it a proton. That's where we get the name. So now, not only are they starting to see that atoms are not indivisible, but they're made up of, at this point in time, 2 things: positively charged protons and negatively charged electrons. And the atom in its most natural state has equal numbers. So if you have 10 protons, you got 10 electrons, and you're neutral. Does that make sense to everybody? Yeah. And the protons are massively, massively, massively heavier than electrons. They are massive. They are big. So neutrons. In 1921, a year later, Rutherford again saw forward, and he postulated the existence of a fundamental particle called a neutron. Now, just really quickly, why would he stop? Because what is wrong with this picture right here? I'm telling you that there's negative charges, right? Just think of these as little magnets, little negative magnets and positive magnets. The negative magnets get to roam out, have a lot of space. But the positive magnets are all crammed together in a super, 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 super tight space. Now, most of us have played with magnets enough to know that if you have 2, a positive and positive, what happens? They repel. So he was like, okay, there's got to be something else. Because if you pack all these positive bowling balls that are really strong together in a space so tight, why are they not repelling each other? Because positive charges repel other positive charges. Well, these neutrons, this is what he hypothesized, could somehow compensate for the repelling effect of the positive charge of protons by causing an attractive nuclear force, and thus keep the nuclei from flying apart from the repulsion between protons. Rutherford's theory of neutrons was proved in 1932, so not even less than 15 years later, by his associate James Chadwick. So the neutron means exactly that. It's neutral, But there's more to it. And of course, the nuclear force took a lot longer to force. And I don't know if you remember last class, if you were here, I talked about the nuclear force. There are 4 fundamental forces in nature. And we discussed the gravitational force. And we all know, we don't really know much about the other ones. But this is the strongest one. So the strongest force in all of nature is called the nuclear force, or they call it the strong force. And that's what keeps the protons together. Now, we'll eventually get to that, but I'd rather just mention it now so you get it in your brain why that's the strongest force possible. And it's funny because that's not what holds us together. What holds us together are electrons, these little guys, But what makes up an atom is, in its core, is the protons. So real quickly is we have an ions. How many of you heard of ions? I remember one time we were talking, it was with Oliver and Devin, my close friends. They were talking about you need to be hydrated and you need your ions and Gatorade. And then we were looking on the back and we're like, I don't see any ions. We were like, what are the ions? Dude, it took us 30 minutes to figure out what an ion was. We're like, what are these ions, So a neutral atom has equal number of protons and electrons balancing out as electric charge. So this is oxygen. Oxygen has 8 electrons, all right? So you have -8 electrons, -8, 8 protons, is plus 8. Together, you got 0. All right, everyone with me? Each atom has a fixed number of protons. Adding or removing a proton changes the element. So you can't mess with protons. However, electrons can be added or removed without altering the element. So an atom wants, in its happiest day, it wants an equal number, but it doesn't need to. It can have different amounts. So if you were to get rid of one, if an atom loses an electron, it becomes positively charged. Because now, instead of minus 8, you have minus 7. Minus 7 plus 8 is plus 1. So if oxygen loses one electron, that's how it becomes positively charged. Conversely, if it gains minus 9 plus 8, if it gains an electron, it has a negative charge. And of course, the more negative charge you have, the more it is. And it sucks because I meant to go to Walmart this morning so I could do a cool experiment, but I was going to do the classic balloon, and get the fur and rub it. And then if you were to take a soda can, is a fun one on the table, and just get the balloon near the soda can will just be repelled like by this distance. It's really cool. And after I did that cool experiment, I was going to explain that when you rub the plastic whatever of the balloon, what you're doing is you're subtracting, you're rubbing off and you're getting rid of layers of electrons, giving it what? A net positive charge. And the aluminum can, by default, because of its metal, has a net negative charge. So you basically made a little magnet. And that's what static electricity is. Like when you build up on the carpet, and you're rubbing on the carpet, you're gaining, this time you're gaining electrons. And then you touch something that has an opposite charge, it's like, ow, you completed the circuit. The next is the size of the nucleus. I mentioned it's pretty small. But to get an idea of the area of the atom relative to the nucleus, you have to think about a massive football stadium as an atom. So I want you to take University of Phoenix or Bank One ballpark, right? And we're going to zoom in, all right? So we're going to take the whole atom and blow it up the size of Bank One ballpark, all right? The electrons would be, and this is relative size. The electrons would be tiny specks of dust hanging on the outermost edge of the stadium. So I'm not talking about the back seat. I'm talking about the back, upper, the roof, like the very edge, like a fleck of dust. That's what an electron is. So what is a proton? A proton, or the nucleus that holds 99% of the mass, would fit on the pinhead of a needle sticking up in the middle of the field. That's how small it is. It has 99% of the mass. So now you can start to get like, okay, atoms are the smallest bit of everything. So you think like they'd be very compact, and size-wise they are. But once you actually blow them up, you realize there's a lot of empty space. Like we are made up of a lot of, on the smallest scale, there's a lot of empty space. So this is how much empty space is in the atom. And all the seemingly solid objects in the material world are made of these empty spaces, held together by electric dust motes. The electrons will hold us all together. Now the billion-dollar question was, if the positive and negative charges attract each other, why did the negatively charged electrons fall in towards the nucleus? So they postulated that there's something going on to hold the positive charges together so closely. Okay. But now you have these negative charges. Negative and positive, they are attracted to each other. Now, yeah, their net thing is 0, but you would think, like, if you thought of them as magnets, they clink together, and there's your net 0. Right. But they're not touching each other. So why aren't they gravitating towards each other? So if an electron just sat outside the nucleus of an atom, it ought to fall into the nucleus, so the atom would not be stable. As the atom collapsed, it would radiate a burst of energy. Now, the obvious way to counteract this tendency for an atom to collapse was to imagine the electrons orbiting around the nucleus, just like planets orbiting around the sun. So this is why Rutherford came up with the orbiting system, because he's like, they got to be doing something, because if they're just sitting there, they're going to fall in towards it. Every math calculation they did had this happen. So they're like, you know what? They're rotating around just like the planets, right? But you guys should know now, since class 2, why did the planets orbit? Because of gravity. Gravity has no bearing here, I mean, you just do the math. You multiply this mass times this mass and the radius, it's going to be nothing, So how did you account for this? Orbital motion involves continuous acceleration. The speed of the particle does not change, but the direction it's moving in does. and both the speed and direction together define velocity, which is what matters. Now, as the velocity of an orbiting electron change, then they ought to radiate energy. And as they lose energy, they ought to spiral into the nucleus. And the theorists, no matter what way they tried, they could not prevent the collapse of the Rutherford model of the atom. So, on one hand, they got so excited because they were like, oh, we're getting this. Oh, we got negative. Okay, we got positive. And then, okay, and they're out here. But then they were like, how do you work it out? No matter which way they did the math, this does not work. Obviously, there's no gravitational pull that's keeping it around. What is keeping electrons out here and the protons in here, and they're all cohesive? Because we're talking about the basic building block of everything, of us, you know? And they couldn't come up with an answer. So scientists could not find a way to hold the electrons in place in their orbits without losing energy and spiraling inward. It is important to note that scientists were misleading themselves. It makes just as much sense to think of electrons as sitting out in space at some distance from the nucleus, not orbiting around it. But they couldn't think that way because orbital motion they understood. Something just staying in one place, even though they knew there was a force, and for some reason it's like, I feel a force, but I'm not moving, didn't make sense to them. So they were trying to work it out using velocities, but they couldn't get that to work either. However, no matter how you look at it, the problem's the same. How do you stop electrons from falling in? This is where we come to Bohr. Rutherford turned to his postdoc student, Niels Bohr. So Bohr is Rutherford's little Padawan, you know, and he had just got his doctorate. And, you know, when you did that, you study under a great, so he got to study under the great Rutherford. And Rutherford, in all his generosity, he goes to Bohr and says, look, Bohr, prove my model's correct. I know it can't be proven according to the laws of physics, but I need you to prove it nonetheless. So he just sort of drops it in Bohr's lap, you know. Luckily for him, Bohr's a genius, you know, which he knew, which is probably, you know, if you're a genius and you're getting old and you meet a little boy genius, you know, you give the problem to the boy genius and see if he can solve it. That was his methodology. Now, Bohr had one major advantage up his sleeve, all right? While most of the physics community was busy arguing and coming to terms with the implication of Einstein and Planck's work, Bohr took the attitude of HOK. That's how one author wrote it, and I just love it. So H, remember, is Planck's constant. Remember, we talked about that last class. Planck's constant is that smallest piece of something, you know. And Einstein proved it again with the light. And that's how he proved about photons, is he says Planck's constant is real. There's a fundamental small constant. Again, everybody was up in arms and not believing. And you see this over and over in physics, where the younger generation pushes it forward. Because the older generation is just arguing. Like, oh, this cannot be, you know, with their full suit and top hat and cane, you know. Where the younger generation's like, okay, well, it's good enough for Einstein, it's good enough for me, you know. So he ran with it. And by running with it, he worked out amazing stuff. He figured if it's good enough for Einstein, it's good enough for him. So he simply accepted quantization as fundamental. So he accepted the fact that energy comes in chunks, discrete chunks. There's some chunks of energy you can't get any smaller. Remarkably, building on these principles, he was able to solidify the atomic model using a simple formula that said that the angular momentum of rotational motion of an object could exist only in quantum units. Given this, only certain orbits would be allowed. What do I mean? Is when heated, the electrons would build up energy and they would jump to another orbit. So he's not just saying electrons are out here in one orbit. He's like, you know what, there's multiple orbits, you know. And this is how they work. So he's just sort of trailblazing. It's just, Bohr is so fascinating because on one hand he was a genius to the highest degree, but he was very kind of maverick. Like he just made stuff up as he went, like ad hoc rules. Like if you look at the history of the electron over his lifetime, it's almost hilarious. Like you could there's volumes of books where they just be making up rules and jimmy rigging. You know, everyone knows what jimmy rigging is. This is mathematical jimmy rigging. There was no in-between orbits since that would require a fractional amount of energy that did not exist. So using the planetary model, this was the equivalent of showing the orbit of Earth as stable along the orbit of Mars, but there's no such thing as a stable orbit in between. So there is no in-between. There's only Earth's orbit and Mars. There can exist no orbit in between. They make a quantum leap. So he said is this, is there's a fundamental small unit, right? This is one of those units, okay? And then this is one more of those units. So if you imagine this like an orbit, which I love this model, you have Earth's orbit and you have Mars' orbit. Now you assume logically that there's orbits in between, right? Like what if Earth, went out a little bit? But he's like, no, nothing exists there. It's either here or here. That's a crazy idea, but he just took what Planck said as, okay, this is fact. He took what Einstein said as fact, and like, bam, now you have it. This is why electrons don't fall in, because they can't. Because they went down and they have energy. So since they have energy, this is their energy. This one has more energy, so it's stuck in, the energy is quantized. It goes like this. Remember the money? You have $5, you have $10. You don't have $1 or $2 or $3 or $4. We all know 5 is made up of 5, but there is no 1, 2, or 3. It's just 5. But there's still a lot more stabilization to go. His formula forbids electrons from crashing into the nucleus since it can't go lower than the lowest energy level. So now he had the planetary model stable. Still had a lot of questions to answer, but he was getting somewhere, and this was a huge breakthrough. Also with his formula, Bohr could readily calculate all the energies allowed for a single electron orbiting the nucleus. What does that mean? As excited as Bohr was about his discovery, how could he prove it? And we're going to explain that other statement. But here he has this novel idea, right? And he works out the math. But how do you prove it? You're talking about you need something in the real world. You need an experiment, right? How is he going to prove this? Well, he was showing a colleague. And the colleague immediately saw a connection that he didn't see. He remarked that his formula's findings prove an already developed branch of science. So there was a whole branch of science that Niels Bohr just was not concerned about. And this colleague knew about this branch of science, which we're going to talk about in a second. And he was like, oh my gosh, this is how we know this is real because you explained all this stuff. So what is he talking about? From the calculated energies, Niels Bohr could calculate the particular frequencies or colors of light that could be emitted from hydrogen atoms electrically excited in a discharge. Like a neon sign, basically. So instead of neon gas, you put hydrogen gas, all right? So this gave credence to the science known as spectrography. Now, I know, Duran, you know about spectrography, or spectrograms, or whatever, Now, these frequencies had been studied for years by other scientists seeking to figure out why these various frequencies and patterns of light were given off by specific elements. What do I mean? Well, here it is. If you take any gas, so this gas, I don't even know what gas this is. I grabbed it from a video I'm about to play. But let's say it's neon, right? And you heat it up with a discharge. Then you take a prism. Now, we all know what happens when you put light through a prism, right? What happens? Huh? Yeah, you get the little rainbow. But this is what you get. If you take a pure element and run it through a prism, you get something a little bit different. Well, there you can see the rainbow, kind of what it looks like. But instead of a rainbow, you got something like this. So here you can see the rainbow, but then you have these really hard lines. Whoosh, red, red. And then you see the yellow and the green, there's blue, and then there's whoosh, a really hard blue line. And there's a space, and there's a whoosh, there's a purple line. So as soon as they saw this, they were like, what the, and they're like, well, you know what, let's try another element. All right, let's try oxygen. A whole nother diagram, totally different. Every element that they tried had a unique set of these. So this is always the same. Think of it like a light fingerprint, Like, it doesn't, I don't even know what gas this is, but let's say it's oxygen, right? No matter what type of oxygen or what you get, or you could have a gas, and you're like, I don't know what this gas is. You heat it up, run it through a prism, and you're like, oh, it's oxygen. That's how they knew it was. But the question was, they didn't understand why. But remember, before scientists understand why, what did they do first? They gathered data. So for literally like 60 years, that's all they've been doing is gathering data, studying spectral line, spectral line, spectral line. And that's what Bohr's colleague knew about. He was like, hey, your formula has a connection to this. So the science of spectroscopy, I keep saying it wrong, spectroscopy, goes back to the early 1800s, where William Wollaston discovered dark lines in the spectrum of light from the sun. So really this all started by sunlight. So if you take sunlight, and you can't do it just easily. Don't go buy a prism and like see if you can see it. You have to do some stuff, and you have to do what's called use a diffraction grating, and you have to kind of clean it up. But what they end up seeing is hundreds of these lines. Now back then they saw 500. Now we know there's upwards of 5,000. You know, you have to get very fine-tuned instruments to see them. But he saw these dark lines in the spectrum of light. So that was the starting point. Once he saw that, then he was like, well, what else gives lines? And that's when they started playing with stuff. And they realized pure elements always give consistent lines. So each color corresponds to a different wavelength of light. And by using the glass prism to spread white light out into its corresponding colors or wavelengths. When the sun's light is spread out in this way, the spectrum revealed is marked by very dark, sharp lines at very precise places in the spectrum corresponding to very precise frequency. So sunlight would always give you consistent results, like these same lines. Doesn't matter where you're at. You know, you're in England, you do it. You know, you go to France, you do it. And the sunlight was giving these lines. So to test and understand why the sun's light had these spectral lines, scientists began to study the spectral lines of other sources of light. They found that these lines appeared in all types of natural light sources, but that natural elements produce these lines consistently. So scientists quickly discovered that every element produces its own unique set of spectral lines. But even before this, they knew about the flame test. So even before this, scientists saw that when an element such as sodium is heated in a burner, it produces light of a characteristic yellow color. So next I'm going to show you a video. And this is a video, if you ever take a chemistry class, you will do this. And depending on what element it is, and you put it in the flame, you get different colors. Very, very specific colors. And I remember, like yesterday, it was funny, the quiz was you get like 4 different elements, and you get them shuffled up. And you and your lab team have to discern what's what just based on the colors. Okay.
We're going to observe what color. This is lithium. Remember that you want to be descriptive with your colors. Calling this red may not be a good description. You may want to say something about the pink tones that are in there. You can see that sodium burns kind of like a bright yellow with strong intensity. This is going to be the test for potassium. See that potassium is a lavender type color. This substance is calcium. Calcium burns a bright red-orange. You saw it there. See that bright
Use a lot of this in the road flare.
red-orange. Different than the sodium. The sodium was more yellow. Where this is more orange. This is barium. Appears to give off a yellow-green color.
Anyways, you get the point.
It gives a
So,
yellow-green color.
oh yeah, you can zoom in. I think that's the last one.
Substance is copper.
Ooh, copper.
You can see this puts off a bright blue-green color. Different than the barium. The barium was more yellow.
All right. So, again, this is crazy. Now, chemists didn't understand why this happened, but they use it as a useful tool, and they still use it today. They have flame tests, but they put them in this box, whatever, and it has a light sensor that does all the sensing for you. So when light passes through a liquid or gas containing the same element, even if the element is combined with others in the chemical compound, the spectrum will show dark absorption lines like the ones with the sun, at the same frequencies characteristic of that element. In other words, the sodium lines will line up with the combination of lines from the gas or liquid. So this explains the dark lines in the solar spectrum. They must be produced by cooler clouds of material in the atmosphere of the sun, absorbing radiation at the characteristic frequencies from light passing through them from the much hotter solar surface. Using this data, scientists were able to account for most of the spectral lines in the sun spectrum by analyzing the spectral lines of known elements. So in English, it means this. Here's the solar spectrum. as they went through and studied all the elements, every element has a very precise line. So they were able to match it up, like, oh, right here, oh, this is hydrogen, okay? Oh, over here, this is oxygen. Oh, this is nitrogen. Oh, so this is, they knew that these were stuff in the atmosphere. And the solar lines were reflecting a combination of these. And of course, in the lab, they can do the same thing. If you know the lines for oxygen and you know the lines for helium, you combine the gases and then you look at the lights, you'll see a combination of both lines. It's like a combination fingerprint. Here's a zoom in, a little bit better. Then you have this Norman Locklear. Norman Locklear used the reverse of this procedure to account for the solar lines that could not be explained by any known elements. So they'd already done all this research. So just from looking at the solar lines, he knew that there were sets of lines that were unaccounted for. Like, what is this? There's no known element that any chemist has published in their paper says this is this. So he deduced that it must be due to an unknown element, which he called helium, after the Greek word for sun, helios. So helium was discovered by looking at lines in the sun, before they even knew about it. It took another decade before they actually found helium. A decade later, when helium was finally discovered, and ended up having the exact spectral line signature as was predicted. What's even crazier is he's not even a physicist. He was an astronomer. Now this goes into that whole other field of spectrography is so important, but it's really important to astronomers. Now why? Anyone? You know now that all elements, their light has a fingerprint, so to speak. Astronomers are looking at the sky. Now if I'm an astronomer, it's great to look at stars, but wouldn't you want to know what they're made of? You know, that'd be kind of nice. That's how they did it. These tools were now like, oh my gosh. Now that's how, a lot of people are like, oh, Jupiter, Jupiter's made of this gas, this gas, this gas. It's a gas giant. A lot of people, just like their planet Earth, they don't know what Jupiter is. Like, really? Have scientists ever been to Jupiter? Never been to Jupiter. How do you know it's all gas? And how do you know what kind of gas it is? Just from looking at it. Now, on Earth, we couldn't do it. We needed Hubble. Because on Earth, you have to look at the whole atmosphere and get all that distortion. Hubble was a telescope out in space. So it got a lot more pure thing. So that's how we were able to know that Jupiter is made up of all the gases that it is. Because we can see the light coming from it tells us what it is. As far as that the planet is made up of gas, we should know that from what? Gravity. Remember, what does gravity tell us? Gravity tells us the mass. So Jupiter has a mass. Yeah, Jupiter's mass is, I believe, it's about 300,000 times the mass of Earth. That's a lot. Jupiter's a beast, okay? Now, no, that's wrong. I got it backwards. Ignore me. Ignore me. Jupiter has a mass 330 times of Earth. That's still a lot, 330 times. But what about the volume? Now, the volume is how much space it takes up, right? So a balloon has a volume, you have a big ball, it has a volume of this. You can calculate the volume just by looking at something, but you have to know the distance. So when you're driving, and I see Duran way down the road, he's like this big. Now, does that mean Duran's this big? No. If I know exactly how far away he is, I can calculate actually how tall he is based off of my measurements here. You could project it out. So we could project out how much volume Jupiter is. Jupiter has a volume of 330,000 Earths. So if Jupiter was a big medicine ball and you open it up, you could put 330,000 Earths in there. That's how massive it is. That's how much volume it is. But its mass is only 330 times our mass. So if any of you guys remember, the next thing besides volume and mass is what? Anyone? Is density. How dense is something? So a balloon is not very dense at all. It's all just air in there. Then you maybe take a medicine ball. Okay, that's still just air, Maybe but you take a bowling ball, that's very dense, right? Very dense. So if you take the size of Jupiter with its mass, you do the calculation, and that's how we know it's all made up of gas. Because if it was solid, it would weigh a lot more. We know how much it weighs. and we know what the volume is, and we know just by looking at it what type of gases are out there, and we know just on Earth that what type of gases are like hydrogen. Hydrogen doesn't, you don't buy a bar of hydrogen. You know, a lot of these gases are very hard to go in solid form. We know their natural state is just gas, you know. But I digress. That's just a freebie. Yeah. Astronomers can use spectrography to probe distant stars and galaxies to find out what they are made of. Once again, simple phenomenon we see on Earth are duplicated exactly in the heavens. The same tools chemists were using to identify elements on Earth could be used to identify elements in the universe. Now, this is how you see it on CSI. They do this all the time. How else can that machine identify drugs and detailed data from blood and saliva? Oftentimes, you can even see the spectrograph. I tried to find an episode. It was like NCIS. I remember it like yesterday because it stuck out in my mind. And it was like, oh, they put it in there, and it looked just like this. Now, this is how the computer shows it, but all it's doing is it's shining light. And from the light, you get what? From the spectral lines, you can now deduce what is in there, you know? And you can know what groups. Cocaine is a drug. It's a molecule. It's made up of, I don't know what. Let's say hydrogen, oxygen, and nitrogen, and, you know, whatever, you know? So that's how, you know, the CSI people are like, oh, this is what we found in your blood. This is what we found in your system, you know? They call it a mass spectrometer. And they're really expensive, and you know, they use them in the labs, but that's how they do traces of drugs in your system. That's how they know all types of stuff. And there's other ways, you know, like they could do this with alcohol and stuff, but they have do a breathalyzer, you know? Chemists have a whole bunch of ways of identifying stuff. But this is how they use it. These lines came to be called Balmer lines, after Johann Balmer. He was a Swiss school teacher. Wasn't a physicist? He was a teacher. He taught like little kids. He worked out a formula describing the pattern in 1885, which just so happens to be the year Niels Bohr was born. Balmer's formula relates the frequencies in the pattern in which hydrogen lines occur to one another. And there he is. Starting with the frequency of the first line in the red part of the spectrum, Balmer's formula gives the frequency of the next Balmer line in the green part of the spectrum. Starting from the green, the same formula applied to the frequency gives the frequency for the red line, and the violet, and so on and so forth. Basically, he didn't know what the lines were, but he was a school teacher, and he was good at math. He worked out a mathematical equation explaining the spacing of the lines. They followed a pattern, like Sudoku, you know, like he figured it out. And he only saw very limited lines, but as scientists discovered more lines in the ultraviolet and stuff, again, his formula predicted them exactly. And a later guy took his formula and extrapolated a little bit wider, and it was able to apply to all lines. And this is how they discovered even more elements, because now they could predict based on what they're seeing, like, okay, well, these lines, and they could, all this just from viewing. They don't know what's going on, but they know this is what we see in the world, and this is how they're using it. Balmer only knew about 4 lines in the visible spectrum when he produced his formula. However, when more lines were discovered in the ultraviolet and infrared, they too fitted the simple numerical relationship. I had the equation up, but I took it out because class 2 scared a lot of people, so I'm not putting any more equations up. So obviously, Balmer's formula was saying something significant about the structure of hydrogen. But what was it? 25 years after the formula, scientists still had no idea why particular frequencies of colors were emitted and why they were spaced the way they were, until, of course, Bohr came. So they should be spread out like a classic spectrum of colors, not like this. Now, I meant to insert a video here. This is really cool, but I'm going to have to get out of here real quick.
The technology at our fingertips can help us do amazing things.
It can help us navigate the world, know which restaurant to book tonight, or know what song is playing on the radio. But when it comes to the actual stuff around us, if you're not sure or just don't know, well, you're on your own.
I'm Damien.
And I'm Dror. I'm excited to introduce SIO. SIO is the first molecular sensor that fits in the palm of your hand.
It scans the molecular fingerprint of an object and provides relevant instant information about its chemical makeup.
You can use it to log the chemical fingerprint, record it, and share with your friends.
Imagine if there was a way to know which watermelon is sweeter.
When is that avocado going to ripen? How many calories, carbs, or proteins are in that shake?
How your plants are doing. Imagine if there was a way to know the chemical makeup of everything we come in contact with. The applications are endless.
SIO uses this tiny optical sensor called a spectrometer, which absorbs light reflected back from an object and breaks it down into a spectrum. The spectrum is then sent to our cloud for analysis, and our algorithms sends back the result to your phone in real time.
Spectrometers are used today in labs around the world, but they're too large and expensive for everyday use.
To fulfill our vision, we need to make a tiny spectrometer that can be mass-produced at low cost.
We recruited an amazing R&D team that redesigned the sensor from the ground up, using low-cost optics and advanced signal processing algorithms.
It took us 3 years and the effort of many talented engineers to create our sensor. We now have a working product and several applications with many more to come.
When you back this project and order your own SIO, you get apps for scanning food, medicine, and plants. With these apps, you can begin exploring the world around you. With any app, the more you scan, the more SIO learns about the things you really want to know.
SIO is our latest design, and we're ready to take it to mass production.
What I find exciting about SIO is that it empowers us all to explore new frontiers right under our noses. You don't have to be a scientist, you just have to follow your curiosity. And every time you scan, you're helping to build the world's first database of matter. That has tremendous implications for research, for medicine, for education, for our food system, and for our environment.
You can also get our development kit and build applications of your own.
Back our project, join our community, and start to SIO.
You just hear that. Now, of course, I gave you the science to back it up, so it shouldn't sound so crazy. Now, they call it a molecular scanner, which it is what it is. But now you know how the molecular scanner works. That it's literally, they were able to miniaturize the laser to the light. And of course, it's going to the cloud, so you don't have a supercomputer and all the expensive equipment they host. And you can know about everything. Now, of course, they're going to market it first for food. Everyone wants to count calories. You know the Weight Watcher people, they're like, a burger is 100 calories. Like, really? There are 1,000 different types of burgers. I'm telling you, the smash burger, the Five Guys burger is not no 100 calories, you know. But now, you could just scan it, and in seconds, it can know the caloric intake. How? Because you're analyzing it on a molecular level. Or imagine your medicine. Oh, your pills get mixed up or whatever. You can scan the medicine and know exactly what it is. You could be in nature. You're like, oh, what plant is this? Let me scan it. And you get the molecular makeup from that leaf to know what kind of plant it is. You go to Whole Foods. You're like, you know what? I'm going to spend $9 on this organic, non-pesticide apricots. You scan it. They're liars. There's pesticides. Because a pesticide is what? It's a chemical. You could read it, you know? I think a lot of organic suppliers are going to go out of business. Because when you empower people with, like they said, it literally will grow. Because the more you scan, the more they learn. And the more they get data. All this from light. Light gives you all this information. It is amazing. So Bohr. So Bohr's formula solved this riddle, and with this equation, Bohr was able to produce with high precision all the patterns of colors. You see, when electrons drop orbit, they emit light at a particular frequency of color. Different colors for different drops of energies. So let me just show you a video. This is from a NOVA special that explains it visually.
But Bohr proposed that unlike the solar system, electrons could not move in just any orbit. Instead, only certain orbits were allowed.
And he had a really surprising and completely counter-physical idea, which was that there were definite states, fixed orbits that these electrons could have, and only those orbits.
Bohr said that when an atom was heated, its electrons would become agitated and leap from one fixed orbit to another. Each downward leap would emit energy in the form of light in very specific wavelengths. And that's why atoms produce very specific colors. This is where we get the phrase, quantum leap.
If it weren't for the quantum leap, you would have this smear of color coming out from an atom as it got excited or de-excited. But that's not what we see in the laboratory. You see very sharp reds and very sharp greens. It's the quantum leap that's the origin and the author of that sharp color.
What made the quantum leap so surprising was that the electron goes directly from here to there seemingly without moving through the space in between. It was as if Mars suddenly popped from its own orbit out to Jupiter. Bohr argued that the quantum leap arises from a fundamental and fundamentally weird property of electrons and atoms, that their energy comes in discrete chunks that cannot be subdivided, specific minimum quantities called quanta. And that's why there are only discrete, specific orbits that electrons can occupy.
An electron had to be here or there and simply nowhere in between. And that's like nothing we experience in everyday life.
Now, of course, this special, they made it like Bohr did all that. As you know, that's how specials are. They just got to throw everything on one person because they got to move forward, So Bohr, if that made any sense, when they get excited, the equation was energy equals Planck, H, times the frequency of light. So when an atom gets excited, it moves up, right? When it falls down, it loses energy. It loses energy times Planck's constant. So that's, each orbit is a unit, a quantum, it's H. You multiply those together and it gives you a frequency. A frequency is that very precise, that's why you get those hard lines. Because in the rainbow, when those frequencies are always the same because each element has a different set of electrons orbiting around it. So they're doing different things. Now the quantum leap, unlike the TV show, now you really understand the quantum leap. Because before, if any of you knew what quantum leap was, quantum leap means like, you go from the Galaxy S4 to the S5. Now that's not even a step. That's like a side step. Let's go from the phone before the iPhone. Before the iPhone was totally rapid. Like that's like a big step. But that's not even what a quantum leap is. A quantum leap is like from the Model T to the Tesla. It's like you didn't just make a jump. Like you just did a quantum leap. That's literally what a quantum leap is that you're here. And you progress and you walk here. Well, the quantum leap, all this doesn't exist. You either go here and then you're here. Like all this space didn't exist. So literally, that is what a quantum leap. And those lines, that's what you're seeing. You're seeing a visual representation of a quantum leap forward. So Bohr's electrons making quantum leaps could be seen visually. That's why the bands are spaced out the way they are. You are literally looking at quantum leaps in energy. So through the careful work of other scientists, so all these other scientists did all this work. Bohr just worked on his atom and then found out that he could calculate all the lines and make sense of them. Bohr was once again cementing quantization in nature. Now his naysayers dismiss his findings as number juggling, but Einstein called it one of the great discoveries. As soon as Einstein said that, everyone's like, okay, fine. Maybe you found something, Bohr's ideas were soon rapidly accepted in chemistry and physics. So now chemistry gets a foundation. Bohr's description of an atom gave chemistry a solid scientific footing for the first time. Now the electrons, these tiny, seemingly immaterial pieces of atoms, are actually at the heart of what the atom sees and feels. So while there are many versions of the periodic table, it was the genius Dmitri Mendeleev who formed the first modern periodic table. He was a brilliant, genius Russian chemist, or I like to call him Dumbledore. As he attempted to classify elements according to their chemical properties, he noticed patterns that led him to the periodic table. The whole purpose of organizing elements into a table is you want to notice patterns. What elements are like other elements? You're trying to find the common thread, how all these things work together. He claimed to envision the complete arrangement of the elements in a dream. This is his quote. I saw in a dream a table where all elements fell into place as required. Awakening, I immediately wrote it down on a piece of paper. Only in one place did a correction later seem necessary. So his brilliant genius came from a dream. Now, I tried to do research on him. I don't know. I believe, from what I could tell, he's Greek Orthodox, but I'm not going to say like he's Christian or whatever. So I don't know what kind of connections you can make there. Like, this is very odd, especially in this day and age. Scientists were not having dreams, and he was brilliant. Like, he was already known to be brilliant. And the fact that he attributed it to a dream seems kind of, kind of strange, the whole thing. So Mendeleev even predicted the existence of new elements due to the gaps in the table, even though they were found and said they would later found and found it had exactly the properties they should have. So his periodic table was so precise that when he laid it out, there were holes. And in those holes, he was like, I predict there's going to be an element that should go here. And it's going to act a little bit like this, and a little bit like this, and a little bit like this. And sure enough, they found an element. Because elements were constantly being found. It was very slow. Yes? Mm-hmm. Oh, no, I do. I just do know it's very hard to find any information about his religious background, So I couldn't comment on what he's about, because obviously historians aren't concerned with that. That's kind of like, I'm sure there's stuff out there, but, I got a lot of material power, I couldn't focus so much, but I would love to. I'm sure there's a book out there that breaks down his life, and that'd be really interesting to see, because for all we know, God did speak to him, And hopefully in the second version of my class, I will add that in there. Now understand that the periodic table is a masterpiece of chemical organization. But the question still remained is, why did it work? Why did the lightest element, hydrogen, have chemical properties similar to lithium, which is 3 times heavier? Or, forgetting that note, why did sodium have similar chemical properties to lithium and hydrogen when it has a mass 11 times hydrogen? And it's almost 4 times heavier than lithium. Like, no matter how they did it, they couldn't do it by weight, they tried to find formulations, but they couldn't find connections. They knew this is like this, but when all the data on them, they couldn't formulate it. That's why they laid them out in a table, because it was kind of like, when you solve a murder and they put all the pictures on the wall. Why? What is it going to do? You want to see dead bodies on the wall? Somehow, if you stare at dead bodies long enough, you're going to solve a crime. So that's kind of like what the periodic table started with, If we just stare at the pattern long enough, we're going to see a pattern and something's going to click. So as beautiful as relationships presented in the periodic table were, there's no scientific understanding as to why it worked. So Bohr's theory stemmed from a picture of the electrons being added to the atom in layers. Okay, we've already seen pictures of this. The first electron would go into an energy state corresponding to the ground state. So the first layer he called the ground state. All right? So this is the simplest atom, hydrogen, right? We've already seen this. The next atom is helium. It would go into the same state. So you have 2 electrons in the first orbit. But Bohr said there was no more room for any more electrons at that level in the atom, and the next one to be added would have to go to a different kind of energy level. So hydrogen, the simplest atom, would have 1 electron in the first shell, and helium would have 2. But lithium would have its 3rd electron moved to a new shell. The first shell would only hold 2 electrons. It was thus filled. So all subsequent electrons would have to be moved to the next shell. Now remember, I already gave you a very effective analogy about what electrons are. So here you have Bank 1 ballpark. You have 2 specks of dust. And you can only have 2. No more specks of dust. After that, you got to go further out. You got to go across the street to the local bar, Gordon Biersch. And that's where the next ones go. Why? Just 2. So an atom with 3 protons and thus 3 electrons should have 2 electrons in the first shell and 2 electrons in the first shell and 1 in the second shell. Well, what about sodium? Sodium has 11 electrons. So according to Bohr, the second shell gets filled at 8. And all subsequent electrons will go to the next energy level. Dang it, what? I pressed the forward arrow too many times. All right, hold on. It's timed. Okay. So now, the first one has 2. Okay, that's weird enough. The next one, which is even bigger orbit, that holds 8. Just 8. Once you hit 8, it's like, no more. This parking lot is full. I need you to move on, Really, but again, you'll see the genius of Bohr and why he was formulating these things. This continued on to copper. Copper has 29 electrons. So 2 in the first, 8 in the next, and then the third shell holds 18. Where these numbers come from, we'll soon find out. But 18. After 18, no more. We're full. We're done. Now you have to go to the next one, and it continues on and on. The third shell would be filled at 18, and the fourth shell holds 32. So I kind of threw in gold. So gold has 2, it has 8, it has 18, then it has 32. Then it has 18, and then one jumps one further out. Now we'll get to why that is. Remember, this was Bohr's, or scientists' first stab at doing this. There was some refinement that had to be going on. So he has no idea why 8 electrons would deem the second shell closed. But then again, he wasn't concerned. He merely matched the science with what he observed. Heisenberg, and we'll talk about him later. You hear him all the time. If you watch Breaking Bad, you've heard about Heisenberg. But Heisenberg was not a meth dealer. He was a brilliant quantum physicist. He would later remark that Bohr had not proved anything mathematically. He just knew that this was more or less the connection. Einstein commented in his autobiographical notes in 1949 when describing the success of Bohr's model that, and you notice element number 99 is Einsteinium. They all have elements, the big elements. There's Rutherfordium, there's Bohrium, there's Mendelevium. Einstein says this insecure and contradictory foundation was sufficient to enable the man of Bohr's unique instinct and tact to discover the major laws of spectral lines and of the electron shells and of the atoms, together with their significance for chemistry, appears to me like a miracle, and appears to me as a miracle even today. That's what I love about Einstein. As brilliant as he was, he could stop and just really see the big picture. Like, this is amazing, like how this is working. And here's Mendelev's periodic table. So you can't really see it, but here you have, over here on the far side, you have the noble gases, and we'll talk about those in a second. Here's what the modern periodic table looks like. Everyone's familiar with this, right? Yeah. And just so we know, a lot of people get confused, like, hey, why is this down here? Yeah, this is just an insert. So really what you're seeing is this. So a lot of chemistry classrooms, if you have a big enough poster, you can line it up. But since you don't have limited space, if you take that out, you can make all these bigger so you can write stuff in it. So that's all this is. So this is really what the periodic table looks like. So again, it was all ordered according to stuff. So the red stain means something, the oranges, there's directions, like as you arrow down, things become more metallic and then less metallic. But let's do an example. Let's take the far left side. These are the alkali metals: lithium, sodium, potassium, rubium, caesium, and francium. All these metals have very similar properties. They're all shiny, soft, highly reactive. They can be all cut easily with a knife due to their softness, exposing a shiny surface that tarnishes rapidly to air due to oxidation by moisture or oxygen. I mean, these things literally, like, how stuff rusts. Like, it oxidizes and rusts and tarnishes, like, in front of you because the air, that's how reactive it is. Because of their high reactivity, they must be stored under oil to prevent reaction with air. Now remember, this is what they do in their pure element. For the most part, they're not always impure, they're mixed with other stuff. They are found naturally only in salts and never as free element. They all react with water. So you put water on them and they're going to sizzle. They all occur in nature and are ordered in order of abundance. So they're actually ordered in order of abundance. Sodium, Na, is the most abundant, followed by potassium and lithium and rubidium and cesium. And francium is a highly radioactive, very rare, you don't want to mess with that. Now, on the other side of the periodic table is the noble gases. Now, most of you have heard of these ones: helium, neon, argon, krypton, xenon, radon. Helium, all our balloons, you always hear about helium. Neon signs. Argon is used in the signs as well, and it's used in lamps. Krypton is used in those, it's used in signs, it's used a lot in lights. Xenon is used in those really bright headlights that when they're behind you, you just wish they'd die, And then there's radon, which is a more rare kind of radioactive. They are all colorless and odorless. They are all highly unreactive, except when under extreme conditions. These things are like non-reactive. They don't react with anything. They're called inert gases. They don't mix with stuff. They don't, like a lot of elements, they always want to combine with something. These things don't. That's why they're noble. It's kind of like they're noble. Like, they are the aristocracy. Like, we don't need other people. We are noble,
Yeah, Switzerland.
Yes, exactly. Now, again, scientists didn't know why they were like this. They didn't understand, and look at the weight. Helium has 2 protons. Then you go all the way down to 86, 54, 36. This is 86 times heavier, or less than that, 86 divided by 2 times heavier. But there was no way for them to relate that. But when they put them on a table, that's when they started to see patterns. But they didn't understand the patterns. So as you can see, the purpose of the periodic table is to establish relationships between elements. Despite this progress, there was no scientific understanding as why. Bohr's atomic structure illuminated for the first time why elements could be grouped together the way they were. He regrouped all the elements on the periodic table. So he took the whole periodic table and reordered it. And that's how it's ordered today. He ordered it by his electrons. So now, if we look at hydrogen, right? Hydrogen has 1 electron in its outer shell. Then you have lithium. According to the rules, it has 2, and then it has 1 in its outer shell. So given that lithium's outermost shell is 1 electron, then it ought to behave rather like a 1-electron hydrogen as far as chemistry is concerned. The Z equals 3 element lithium, it does indeed show some chemical similarities to hydrogen. So now you can visually see why lithium would act like hydrogen, because they both have 1 electron in their outermost shell. That's probably why he thought 2 were in the inner one. Then there's sodium. Sodium is beneath that. Again, 11. That means there's 2, and then there's 8, and then there's 1. So just like lithium, it's got 1 electron in its outer shell. So it has chemical properties similar to hydrogen and lithium. If you look at the noble gases, all the noble gases have full outer shells. So another thing Bohr said was that an electron wants to have a full shell. It is happy with full. Now, why 8 is full? Wasn't really sure. But if you're full, then you're happy. Because if you have 8, you're like, I don't need any more electrons. You're not taking any electrons. Like, I'm happy, So chemistry, what is chemistry concerned with? Chemical reactions, DNA, proteins, they all want to know the combinations, all pharmakeia. So why does carbon react with hydrogen in such a way that 4 atoms of hydrogen attach to 1 of carbon and make a stable molecule of methane? Why does hydrogen seem to always come in the form of molecules, each made of 2 atoms, while helium atoms do not form molecules and so on and so forth? Well, one of them you should know already. Why do some elements seem to always come partnered with other elements, and other elements are always by themselves? The answer came with stunning simplicity with the electron shells. When 2 hydrogen atoms come together, they form a molecule so that they share their 2 electrons in such a way that each feels the benefit of a closed shell. So here's hydrogen, right? It's got 1 electron. What does it want? It wants a full shell. What's a full shell? 2. Hydrogen is never found in its normal state in nature like this. It's always found as H2. So if you take another hydrogen, well, there's the one that's missing. If you take another hydrogen atom, if you look at them together, they can share electrons. So look at the circle. One of them, see the line? This hydrogen atom thinks it has 2. So it's happy. Bohr said you are happy being full. And the other hydrogen thinks it has 2. So they're both happy. It's very stable. It's not silly to say happy, but that's the easiest way to analogize it, Now you take something like oxygen. Oxygen has 1, 2, 3, 4, 5, 6, 8 electrons. So 2 are in the middle, and then 6 on the outside. Remember, it wants to be full. It is not happy. It's like, I need 2 more. Well, guess who's going to come along? In nature, what do you always find? Mr. Hydrogen. He's like, hey, I'll share with you. Bam! Look, hydrogen's happy. I got 2, I'm happy. I got 2, I'm happy. Look at oxygen. It's got 1, 2, 3, 4, 5, 6, 7, 8. Happy. Everyone's happy. Sharing is caring. Kindergartners can learn a lot from atoms, And what do you see? Water. Yes. That's why we see so much dang water. It's a very nice molecule. What about carbon? Carbon only has 6 electrons. So it's got 2 in the middle and 4. So you know what? It needs to watch Joe's series because it's literally really depressed. Like it really it's half full. Half full electrons are really reactive. Chemists didn't know why certain things were reactive. Now you know. It's half full. It's like, dude, fill me up. You know, it's like a car. Fill me up. So guess who fills it up usually? Hydrogen. You get 4 hydrogen there. Bam! Carbon's full. All the hydrogens are happy. Everyone's sharing. That whole outer shell is being shared by both. And what do you have? You have methane. Methane's, whether you know it or not, methane deposits, methane gas, that's hugely predominant naturally. Oh, and this is cool. I just happened to share this. The most dominant form of hydrogen is not H2 in the whole universe. 98% of the universe is made up of H3. So they really share. Look at that. So each one has 2. If you intersect them, so 3 can share, because you think only 2 can share, but it's easier to write this if you do it 3-dimensionally, because at this point it's literally like a triangle. And if you go online and look at molecules, they're usually 3-dimensional. But this is how that works, And I was going to go crazy, and actually I was trying to put together rubber, like a complex molecule, but it just got too crazy. Because basically you keep connecting stuff. It's like Connect4 on steroids. So in other cases, now the way I showed you is a nice way, very simply, to explain stuff. It's the sharing. But this is how you generally don't think of it as sharing. Here's the other way to look at it, is to imagine sodium, right? Imagine we took away an electron. What would happen? Everybody? Remember what happens? Huh? Yeah, it's going to be an ion, and it's going to have a net positive charge, right? Now we're going to go over to chlorine, and we're going to give it an electron. So now it's got more negative than positive. So it's going to have a net negative charge. So you have a positive charge and a negative charge. Same dang thing, but instead of sharing, you think of positive and negative. Attract. So that's generally what you always hear, but you can think of the same thing as they're sharing. Or you can think of it as things get more complex, it's easier to think of it as charge, taking away positive and negative. Chlorine, by gaining an electron, becomes negatively charged ion. Since positive and negative attract, they will naturally combine. Here's Mendelevium from Mendeleev. The energy transition between these shells, and as you can tell, there's more to the picture. This gives you a clue of what's coming up next. Because here you have 2, 18, 32, and then 31. Remember, Bohr said you had to fill up the whole shell. But this one then went to the next shell and did 8, and then 2. So it's not as simple as that. There's a little bit, there's some more shells, and he'll figure that out. But there's still a definite order. There's a system, and we'll go over it. Like Mendeleev, Bohr's table didn't merely predict the existence of missing elements in his table, but he was able to predict with detail the properties of these missing elements. So again, he filled in the periodic table, and he could see holes. Like, okay, we know there's going to be something here. It's going to have 25 electrons, and it's going to act like this. It's going to be this reactive. Blah, blah, blah. He knew everything. And sure enough, when they actually found the element, they pieced it in. So we're discovering elements by looking at light in the sun. We're discovering elements by grouping stuff. And now we're discovering elements now that we know that we can count protons, it's like, look, if you know every time you add a proton, you get a new element, okay, well, you get a lot of elements. Now, there's limits. Obviously, you can't go to infinity, and there's reasons for that. We now see how chemistry was put on a solid footing, and how all chemistry needed was a quantum cookbook, so to speak. So chemists, all of life, all of nature, everything we know is dependent on this model of the atom. Now, it doesn't have to make sense. As a chemist, you don't need to know why there's only 8 and why there's only 32 here. You just need to know why it works. And you need to know, and the physicists also gave them more than how to do all these connections and how they work, but they gave them energies and this and that, and they were able to calculate, and that's how they do simulations, and that's how they form drugs. But the chemist has no idea of the why. Once we get into the why, then we get into the dead and alive cats. But that's the whole principle. That's the core of quantum physics, is to try to explain this. Because we get now why they don't fall into each other, okay? Because nature has limits, and we don't really get how this force is keeping all the protons together, but we can surmise, okay, there's some type of force. We don't even know what it is. It's holding them together. But how in God's name do you explain the numbering? You have 8, you have 32, and they combine, and you share. Chemistry needed this information to push forward. Physicists set all the rules and chemistry took off from there. Chemists don't need to be concerned with the why it all worked the way it did. The simple fact that it worked was enough for them. So this I just threw in because, again, I really don't think people realize the magnitude of the size of the atom. So if you had a spoonful of sugar, right, that equates to 1 mole of carbon. If you remember last time I went over a mole is, what was it, 6, 7 trillion atoms, or just something stupid. Really big number. Oh, there it is right there. 23 zeros, so a trillion. So let's try to put that number in perspective. Huge numbers are often called astronomical, for good reason. Those numbers are indeed big, so let's try and find a comparison in astronomy. And I mentioned this a while ago, but here's just the numbers. So astronomers believe the age of the universe is roughly 15 billion years. You've all heard that, right? That's 15 times 10 to the 15. The number still doesn't come close to the 23rd. So let's use a smaller unit of time. Let's use seconds. So if the Earth is 15 billion years, it's actually 32 million seconds. No, a year contains 32 million seconds. So 15 billion years is 45 times 10 to the 16th seconds. We're still way off of the number of atoms in a spoonful of sugar. So I want you to imagine an alien watching our universe develop from the Big Bang, right? And the alien has a pair of tweezers. And every second, the alien plucks 1 atom out of the pile. That's all it does, for every second. For 15 billion years. For all the length of the created universe, according to science, it removes 1 atom at a time every second. Well, after working steadily for 15 billion years, the alien would have just removed about 1/1,000,000th of the carbon atoms. Not 1%, 1/1,000,000th. So you see how many are in there. It's a miracle that we understand anything about atoms and that we can find a way to bridge the gap from classical Newtonian physics to quantum physics. So the number of protons in the nucleus decides what element it is. The number of electrons which by default is the same as the number of protons, determines the chemistry of the element. So the electrons determine the chemistry. So like I said, if the shell is half full, it's very reactive. Hydrogen only has 1 and it wants 2. Hydrogen is always bonding with something, but it's easy. It wants 2, it's got 1. So electrons are all about the chemistry, but the protons are what make up the element. Atoms can have different amounts of neutrons. Now neutrons, we haven't got there yet, but I just figure I'd throw it in there because we're going to get to that. But when you have different number of neutrons, that's when you hear the term isotopes. So ions is different number of electrons. Isotopes are different number of neutrons. So carbon-14, how many have heard carbon-14? That's what they use in all the radio. That is an isotope of carbon. So carbon has 6 electrons and 6 protons. 6 plus 6 is 12. So carbon-12 is your standard. Carbon-14, which is a radioactive version of carbon, it's just like carbon, but it has 2 extra neutrons in the nucleus. That's what makes it a completely different but same thing. Tritium. Remember in Spider-Man, tritium? It's like so expensive, it's the rarest element, and I have to be a billionaire retard to buy it, you know? All tritium is an isotope of hydrogen. I think Hollywood likes to mess with people, you know? And so hydrogen has no neutrons, right? It's just a proton and an electron. If you have a hydrogen atom containing 2 neutrons instead of regular hydrogen 0, that's what's called tritium. If it has 1, it's protium, you know? This is where have you heard of heavy water? You know, they use that for the early nuclear weapons. That's what it is. It's heavy water. So you have H2O, and the hydrogen is extra heavy because it has extra neutrons. So again, go back to the analogy of the stadium, right? The pinhead of the needle has little tiny protons. Here you have 10 protons, right? Don't worry with electrons. It's 10 protons, 10 electrons. 10 protons, you have neon. Everyone knows what neon is. It's a gas, right? If you just add 1 little microscopic minuscule proton, you have sodium. Like, you go from gas to salt. That's the only difference between things, is these 1 little proton. If you add 1 more proton, you get magnesium. You get your vitamins. You add another proton, now we're to my laptop. We're to aluminum. Just little tiny, I mean, I don't know about you, maybe it's just me, but it just boggles my mind how that's what makes one thing another thing. Is this, in this little tiny compact nucleus, you had just a little tiny proton and it just changes what it is. Oh, I think I got 1 more. You had another one? You get silicon. You get Hollywood. Or I meant chips. I meant chips. Pentium chips, you know. Or how about platinum? Everyone loves platinum. You add one little proton, you get gold. I'd rather have gold. Platinum used to be higher priced, but now it's not. It's like half the cost of gold, which is still really expensive. And there's tin, you know. Neutrons and protons have nearly the same mass as each other, but each is about 2,000 times as massive as an electron. The more massive a nucleus, the more variety of isotopes. Tin, for example, has 50 protons in its nucleus and 10 stable isotopes. All this goes on in a volume that is almost unimaginably smaller than the most unimaginably small atom. So, and this is really interesting because I shouldn't have actually put that other spec because that's what people always quote, the stadium. The stadium is easier for people to understand, but this is a more truthful statement. So a typical atom is 10 to the negative 10 meters across. Very small, obviously. The nucleus is 10 to the negative 15 meters. Now again, to get that scale, here is an actual analogy that's real. So volume goes as the cube of the radius. So volume is, feet squared. Cubic centimeters, cubes. We multiply the exponent by 3 and find that the volume of the nucleus is 10 to the 15 times smaller than the volume of the atom. What does that mean? If you take an atom, now we're not doing the stadium, and you blow the atom up to the size of the entire Earth, or if you were thinking of the atom as the size of the Earth and then blow up, I wrote this wrong. So the apple is the atom, and you blow up the apple to be the size of the Earth. Your original apple is how big, how much area, what the volume is of the nucleus. So that's a whole different thing than the stadium. So you imagine the whole Earth. So on the very edges of the Earth are specks of dust that are electrons. And 99% of the mass is in the volume of the same size apple in your hand. That's a lot of empty space. No matter how you look at it, it's crazy. Radioactivity. Why are things radioactive? I mean, we all know what radiation is. Most of us have never experienced it. Well, not on the level like movies. We actually experience it all the time. Whether you're X-rays, every time you turn on the microwave, you're getting small amounts of radiation. Your cell phone, small amounts of radiation. But you know what I mean. We're talking about the dangerous radiation. Rutherford and his colleagues were investigating the nature of radioactivity when they discovered a very curious property of the atom, or rather, its nucleus. Radioactive decay, as it became known, had to involve a fundamental change in an individual atom. We now know it involves the breakup of the nucleus and the ejection of parts of the nucleus. So when a radioactive material decays, the atom literally breaks up. And as you know, if a proton happens to leave the nucleus or get ejected, what happens? You change it to a completely different element. Just like he was able to take nitrogen and become oxygen. Carbon-14, it's radioactive. It decays into nitrogen. Nitrogen is the next element over this way, has one less proton. So what they found was that this phenomenon seemed to be completely unaffected by any outside influence. Heat the atoms up, pull them down, put them in a vacuum, in a bucket of water. The radioactive decay continues undisturbed. There seemed to be no way of predicting exactly when a radioactive atom would decay. So, even before you read that last statement, so they see that atoms decay. And you're about to see in a second, they have what's called a half-life, So if you have 1 trillion atoms, in a certain amount of years, depending on what it is, you're going to have half that much. No matter what scientists have ever done, it's still true today, and they still try experiments. There's no way of understanding why it decays. Like you think, what's the ticking mechanism, And this starts going into the weird nature of quantum mechanics, is that there is no reason, just like there is no reason why energy is quantized. It just is the way it is. And it's kind of like the cat alive and dead and the light switch on and off. The only common denominator we found is that if you look at a large number of radioactive atoms, so that's obviously, no matter what you do with atoms, it's a large number, trillions and trillions and trillions, a certain proportion always decays in a certain amount of time. So we can never say when they decay, but we know over a certain amount of time, for a certain radioactive element, you will lose a certain amount. That is how much we know. So there's plutonium. Everyone knows what plutonium is. It's got 94. For every radioactive element, there's a characteristic time called a half-life, during which exactly half the atoms in a sample decay. Now, when I say decay, I mean the atom falls apart and becomes something else, So carbon decays into nitrogen, it's no longer carbon. Radium, for example, has a half-life of 1,600 years. A radioactive form of carbon, called carbon-14, has a half-life of little under 6,000 years, which makes it useful in archaeological dating. Radioactive potassium decays with a half-life of 1.3 million years. I don't know if that's 1 point or 1,300. I don't know if I wrote that right. Despite, they vary, Now, since they didn't know what made one atom disintegrate while its neighbors didn't, they used the discovery as the basis of a statistical theory of radioactive decay, using Now, I don't know the right way to say that, because I've heard it say actuary tables, and I've heard it say accurial tables. Does anyone know? This is what insurance company use. Anyways, I just thought I asked. That's what I think, actuary. Using actuary tables like those used by insurance companies. So insurance companies know that though some people they insure will die young, and their heirs will receive far more than the insurance company than the premiums paid on it, other customers will live long enough and pay enough in premiums to compensate. So Dave Ramsey always says, look, insurance companies are the most stable stocks. They don't go up a lot, they don't move a lot, because they have hundreds of years now of these accurial tables. They know. They've done all the statistics. They know that you could pay in for a week and die, and I pay you millions. I lose a lot of money. But then for every person like that, there's so many people, who pay in for 50 years before they die. So they end up paying more in than they got out. So it's basically just statistics. If you know enough about enough standards, you can know you won't lose money. Insurance companies rarely lose money. Even Hurricane Katrina, insurance company have to pay out trillions. It's all worked in. The math is all there. They know how often storms hit. They know how often cataclysmic storms hit. That's why they really hate frauds. You throw off their tables. They even have calculations for that. Without knowing which clients will die when, the actuary tables enable the accountants to balance the books. So in the same way, statistical tables allowed physicists to balance the books of radioactive decay, provided they are dealing with large collections of atoms, which isn't hard. So an interesting feature is that radioactivity never quite disappears from a sample of radioactive material. So for the trillions of atoms present, half decay in a certain time, right? Over the next half-life, exactly the same, another half decays. So when you're dealing with numbers this big, and if you do it on a spreadsheet and just try it, you'll really never get to zero. Just keep it smaller. It gets small pretty quick, but then it just, eventually maybe, you'll get there, but for the most part, you're just not in your lifetime, or any lifetime. The number of radioactive atoms left in the sample gets smaller and smaller and closer to zero, but each step towards zero takes it only halfway there. Rutherford and his colleagues imagine, of course, that someone would find out exactly what made an individual atom decay, and that this discovery would explain the statistical nature of the process. So here, I'm about to show you all the isotopes of carbon. It's kind of interesting. So regular carbon is what? C12, right? Carbon has a whole bunch of isotopes. So there's C8. C8, which means it has 6 protons and 2 neutrons. So it's missing a whole bunch of neutrons. It's missing 4. It has a half-life of 2 trillionths of a billionth of a second. Very short.
Yeah.
This stuff decays And you have C9, 126 milliseconds. So 126.5 thousandths of a second. That's a lot longer than a billionth of a trillionth of a second, C10, almost 20 seconds. 20 seconds. Every 20 seconds, half of the atoms decay. Then half, then half, then half. C11 is 20 minutes. Then you have carbon, carbon-12, stable. If you add one more neutron, stable. But carbon-14, that's what we use for our dating, 5,730 years is how long it takes for half of them to disappear. C16, you're back down to seconds, 2.449 seconds. C17, 193 milliseconds. 18, 92 milliseconds. 46 milliseconds. 16 milliseconds. 30 nanoseconds. So remember, a milli is 1,000th. A nano is a billionth. And then it goes back up to milliseconds. So again, if you look at this, scientists couldn't make any sense of this, But in the equations of quantum mechanics, all these numbers will jump out and they make sense. I just thought I'd throw that out there to give you an idea. This is just carbon. Now, carbon is one of the ones that has the most stable isotopes. Depending on the elements, some elements only have 1 or 2. Usually they have at least 1 or 2. Some of them have 10 or more. So Einstein took the statistical nature into the Bohr model of the atom to account for the details of the atomic spectra. He too anticipated that later discoveries would remove the need for the actuary tables, and they were all wrong. So he took the Boltzmann. Remember Boltzmann, the entropy I discussed last class, that miracles are possible, and remember he killed himself before Einstein actually, brought it to light? Well, he used that same math that proved the theory of entropy, the law of thermodynamics, and used the same math now and applied it to the atom. And once again, it worked. It worked just like you would an insurance company actuary table. But Einstein hated the fact that he never thought in his million years that the story would end there, which it does. There's no way we can know when the cat will be alive and dead. It's completely random. Just like there's no way to know when an atom will decay. There's some other really cool things, maybe you've heard of it, Zeno's paradox. Anyone heard of Zeno's paradox? Okay, well, we'll get to that. The energy levels of an atom and an electron, the energy levels of an atom or an electron in an atom can be thought as a flight of steps. So the depth of each step is not equal in terms of energy. The top steps are closer together than the bottom steps. So Bohr showed that in the case of hydrogen, the simplest atom, the energy levels could be represented in terms of a staircase, where the depth of each thread below the top of the staircase is proportional to 1 over n squared, where n is the number of each step from the bottom. The transition from level 1 to level 2 on this staircase requires that an electron takes in exactly the amount of energy, hv, required to move up that step. And I'll explain this in a second. If the electron falls back to level 1, the ground state of the atom, then it gives up the same amount of energy. And it looks like I did not put the picture. Hold on. So remember the energy chunks? If you think of them as a staircase, the staircase chunks are uneven. This isn't quite to scale. But that's how, when the atom falls, and that's how it's hard to explain without the picture. But just imagine an uneven staircase. You go up a step, and then there's a big step. And there's maybe a little step, and then there's a medium-sized step. That's how much energy it takes when they get excited to move up to the next energy level. So when they fall down, they emit that much energy back out. And that's where these frequencies of light were calculated. I'm not sure if that's a good example, but unfortunately, apparently my picture was lost. I have like 10,000 pictures. And that basically rounds it out. I don't want to go too far. There's no way an electron can absorb less energy because there's no in-between step on which it can rest. The only way in which a level 2 electron can emit less than a quantum of energy because there's nowhere for it to jump down except to the ground state. And I don't even want to go over because there's no picture, This is all gibberish. So in a hot gas, atoms are constantly colliding with one another so that electrons are excited to a high energy level, and then they fall back, radiating bright spectral lines as they do so. When light passes through a cold gas, the ground state electrons are raised to higher energies. So basically everything is with these little invisible quantum steps, and that has to do with the shells. And I guess the next section is when I start to break down carbon-14, For this reason, since carbon-14 dating has been talked about so much in Christian circles due to its possible inaccuracies, I wanted to take a moment to break it down so you can understand why carbon-14 dating can be so easily wrong. Because they're like, oh, the shroud is this old, or oh, here's Jesus' bones. He was actually born 50 years ago. Like really, So that basically concludes our class. So this was, I know this was a more science-heavy class. There wasn't as much gotchas, whatever. Next class will be a lot more, because that's when we start getting some crazy stuff. But we had to break down, dang it, I forgot you can't see my screen. But we have to break down this first. But still, I hope you really got an appreciation for what we are. Like, you know, this is what we are, and this is how it works. And even though it's still weird, you know, it's like the little electrons and their little shells. Like, why? Why does this shell only hold 8? I mean, what is a shell? Now, you'll learn later that they don't really orbit like this, and then chemists come out with all these different shapes. But the same mystery remains, is why, you know. Because chemists are like, oh, no, that's old school, you know. It's not 8 in a shell. The eight actually go out in a balloon. Like, literally, it's like a balloon, you know. 4 in this balloon, 4 in this balloon. Well, no reason why, you know. Any questions? No. But the other cool thing is, again, see how principles, it's all about precept upon precept, like literally. You know, like seismology, like we know sound waves can detect patterns beneath things. Like ultrasound uses a ultra high frequency sound wave. And, you know, I saw my baby, you know, it's in the tummy, and they did 3-dimensional thing, you know. They shoot stuff into the ground now, and they can see what's under the ground by waves. Well, what's funny is because they launched this really high-end probe, right, to analyze the sun. It's like $400 million, right? And they got the images, and it was like it was broken, basically. So they're looking at the sun, and instead of it being in focus, like they zoom in, like you can see it. It looks like static. Yeah. Whatever. And it was like this big hoopla, blah, 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 da, da, da. So they put up another satellite. This one was like $800 million. You know, this was just recently, like 2010, right? Same dang thing, you know. And here's the irony, and this is all recent, within the last decade, is they realized it wasn't broken. What they're seeing on the suns was not, what the surface of the sun isn't static. It was actually sound waves. You're seeing sound waves. And as soon as they saw sound waves, they know all about that, seismology. So looking at the sound waves, they were then able to extrapolate the structure of the sun. Now, we know more about the structure of the sun than we know a lot about the structure of the earth, like the core is iron, this and that. But we have detailed imagery because the data is there. It's just coming out at us, these sound waves. That's how we know how the structure of the sun. The sun has 330,000 times our mass, but it has 3.3 million times our volume. So it is really light. Like density-wise, the sun is 0.5 grams per cubic centimeter. Jupiter is 1.5 grams per cubic centimeter. And the Earth is 5. So we're 5 times denser than Jupiter and 10 times, right? 10? Yeah, half, yeah. 10 times denser than the sun, you know? But the sun, we know all this because we studied sound waves. We understand how sound moves. We see that. We understand light. Or like solar flares. This is something we'll get into later, but you may not know about solar flares, but solar flares are like, they eject, I mean, it's crazy. They eject like a bomb wave at us, you know? Yeah. And if a solar flare ever hit us, a strong one, directly, it'd be like that show, Revolution. What was it, Revolution? It would wipe out everything. It would destroy all electric circuits. We'd be back in the dark ages. We have to start over. You heard of an EMP? Yeah. You know, that's what it is. A worldwide EMP. And one almost hit us, like in 2012. Yeah. Because we could project it. That's why one of the top things they're working on, and they've already have it, and we're going to go over it, is a quantum telescope. A quantum telescope can see into the future, meaning this way. I'm not seeing the future like sci-fi. It can look at the sun, and we can see a solar flare before it happens. Now, what does that mean logically? Like, we don't really see it before it happens. If something happens on the sun, we all know that the light has a fixed speed, right? Yeah. So, as soon as we see a solar flare, it took 8 minutes. Earth is 8 light minutes away. It took 8 minutes for us to see it. Now we can look into the future. So looking into the future using a quantum telescope, you're not really seeing in the future, you're seeing the real time. Yeah. You're seeing real time faster than light. That's what that means. So imagine like Vega. Vega's like what, 50 million, whatever. Like, let's say we found a planet that was 50 billion light years away. As soon as we see that planet, we're looking at 50 billion years ago. Or, we don't know what they look like now. For all we know in the telescope, they're a thriving civilization. But in reality, it's just dead. With a quantum telescope, we can look at a planet that's 50 billion light years away, and we can look at it now. So maybe with a telescope, it's a dead rock. But we look at it then, and it's a thriving civilization. Because it took 50 billion years from the dead rock to come into a thriving civilization. So that's kind of some of the things you see weird about the quantumness, is you start being able to bend rules, because you can't go faster than light. So how can you see faster than light, Well, there's certain rules, just like in the movies. Like, I'll give you a hint. One of the rules that can't be violated is causality, right? Yeah. So you can't do stuff like in the movies. You can't see yourself die and then stop yourself from dying. So the whole point of the sun is, we don't have any causality. Because if we're going to see what's happening in real time, you can't stop it from preventing it from happening, right? So it makes sense solar. But the military, they're interested in this because they don't want all their machines and weapons to go down. The military is working and putting billions of dollars into not only quantum computers, but imagine if we could see China or Russia launch nukes before they happen. We could see Iran, some crazy Iranian dictator, launch a missile before it happens. Now, I just told you, you can't see something in the future and change it. That's why it's easy to imagine whatever. But I'm also going to show you experiments where you can set things up in a way where we could see Iran launch nukes before they actually happen, as long as we weren't able to change the outcome of it. Now, it's still a huge advantage militarily. Like, yes, it'd be nice to see it before it happens and prevent it. But if you knew it was going to happen, and there's a certain scientific principle, like there's certain rules that you just can't break, I'm telling you, it starts getting really trippy, And I'll actually show you experiments where you actually see these things happening. And you're like, what the heck? And again, it all has to do with the dang cat being alive and dead. I kid you not. So that concludes. Thank you for coming. I promise you more cooler stuff on our next class. But we had to learn about atoms. It's part of one of those things,